Well, hello there. Today we're going to be talking about the force of gravity between masses. Today you will learn how to calculate the force of gravity between any two objects. We're also going to learn how to calculate the universal gravitational constant. How about gravity between Earth and you? Well, let's imagine that you are right here. So there you are. There is this certain amount of gravity between you and the center of the Earth. And we have defined that to be your weight. But the reason there is this gravity between you and the Earth is because the Earth has mass, and so do you. And this is a very simplified version of a much more complicated equation that we're going to be learning about today. Because any two objects that have mass, there is a certain amount of force between them, and it is the gravitational force. The moon, which I've got drawn out here, stays, not moon, let's try this again, moon. The moon stays in orbit because there is a certain amount of gravity between the Earth and the moon. But we know that this equation isn't going to work exactly because gravity, G, as we've discussed earlier, is not the same when it gets clear out here to the moon. As far as you get farther from the Earth, gravity, G, the acceleration due to gravity, drastically decreases. So, how do we go about finding that? Well, that's found here, alright, by universal gravitation, meaning between any two masses, say mass 1 and mass 2. And that's what we've identified here, mass 1, mass 2. We can find the force of gravity, alright, how much attraction there is between these two, due to the radius squared in this universal gravitational constant here called capital G. Let's go back to the previous slide. What I want you to understand is this force, the gravity, alright, the Earth is pulling down on you. But we know, according to Newton's third law, that you're also pulling on the Earth just the same. You probably never thought about that, but gravity goes both ways. You're attracting the Earth the same way the Earth is attracting you. Now, why then, why do we feel this huge force? Well, the force, let's say, for example, my force is 230 pounds. That is the force that's pulling me down. That means there's also a force that I'm exerting on the Earth pulling up on it. Well, because the Earth is so massive, let's look at our equation here. F equals m times a. Alright. Because the Earth is so massive compared to me, to put a force of 230 newtons or pounds right there, and to give the Earth the mass, right? The Earth's mass is huge. The acceleration the Earth feels is very, very small because that mass is so large. Just the other way, if I put 230 pound force on me because my mass compared to the Earth is very small, the acceleration I feel is very large. So let's go back and talk here a little bit more about this universal gravitation. G, in this case, is 6.67 times 10 to the negative 11th meters cubed per kilogram seconds. Well, G is a very, very small number. And it is this number that's necessary for the gravity to be correct when we're talking about any two masses. Right? This is what is the correlation here between these two. Gravitational forces are small in comparison to other natural forces. For example, electrical forces. right? Or nuclear forces, that's specifically the strong force, or even the magnetic force that we've felt as we were working with magnets. We know that two magnets would push each other away, so they were stronger. Those little magnets were exerting a force stronger than the gravity, because they would, if you had them next to each other long, they would plop each other off. So gravity is a very small force when you want to compare it to the other natural forces, such as electrical forces, nuclear forces that happen in the nucleus, and even magnetic, which is one I don't have listed up here. Well, an example. How would we go about finding gravity then between any two objects? Well, let's say that we want to find the force of attraction between a male and a female. Well, to go about this, we would simply plug them into our equation, because this male and female are just simply masses. And we would go about finding that force between them by taking 6.67 times 10 to the negative 11th. That goes in for G. I'm now going to put in mass 1, which is the 100. I'm going to put in mass 2, which is 75. And the radius squared, or let's say the distance between them. They're sitting in two seats that are 0.9 meters apart. Well, when we calculate this, the gravitational force between them turns out to be 6 zeros, and then a 6 newtons. So as you can see, the gravitational force of attraction between a male and a female, or I'm just using a male and a female for example here, is infinitesimally small. Alright, infinitesimally small. But there is a certain amount of gravity between these two objects, and I think that's important here. It is very small. What would you do to make this gravity increase? Well, notice we're talking about some very small masses here. Very small, specifically when you compare them, let's say, to the size of planets or a moon or whatnot. Well, here's what I want you to have done before you come in tomorrow. I'm giving you two different masses. I've given you a new radius, and I want you to go ahead and now solve for the force of gravity between these two objects. Once again, it is the force of gravity. It's not exactly the weight, because the weight is the force of gravity acting on something due to Earth's gravity. This right here, we're talking about just the force of gravity between any two objects. Hey, I hope this has been informational and instructive. Hopefully you've enjoyed it, and I'll see you on the flip side.